Here's something most people don't realize. Everything we can see in the universe, every star, every planet, every galaxy, every cloud of glowing gas, makes up less than 5% of what's actually out there. The other 95% is invisible. We can't see it, we can't touch it, and after decades of searching with our best instruments, we still can't say exactly what it is. It doesn't emit light, it doesn't block light. The only reason we know it's there at all is because of what it does to everything around it. Or something massive, something real, is quietly holding galaxies together, bending light across billions of light years, and shaping the entire structure of the cosmos. And it is, right now, one of the biggest unsolved mysteries in all of science. By the end of this two-part video, you'll understand exactly what that invisible 95% is doing, why it's so hard to pin down, and why some of the smartest physicists alive are quietly worried that our entire picture of the universe might be missing something fundamental. Let's get into it. In the 1970s, astronomer Vera Rubin was studying how stars move inside spiral galaxies, and she found something that shouldn't have been possible. Stars near the edge of a galaxy should orbit much slower than stars near the crowded, massive center, the same way outer planets in our solar system orbit the sun more slowly than Mercury does. That's basic gravity, confirmed for centuries. But that's not what Rubin saw. Stars at the edges of galaxies were moving just as fast as stars near the center. Based on the visible mass alone, all the stars and gas we could actually detect, those outer stars should have been flung off into space entirely. The galaxy shouldn't have been able to hold itself together. Something invisible was providing the extra gravity needed to keep those galaxies intact. Not a small amount. Rubin's calculations suggested there had to be roughly 5 to 6 times more mass than we could actually see, wrapped in an invisible halo around every galaxy in the universe. What made this especially hard to dismiss was how consistent it turned out to be. It wasn't just one strange galaxy. Rubin and her collaborators checked dozens of spiral galaxies, and nearly every single one showed the same pattern: stars at the edge orbiting far too fast for the visible mass to explain. Whatever was providing that extra pull wasn't a fluke of one unusual system. It appeared to be a universal feature of galaxies themselves. We call this invisible mass dark matter, and the name is almost comically honest about how little we understand it. It isn't dark because it's black or shadowy. It's dark because light doesn't interact with it at all. It doesn't reflect it, absorb it, or emit it. It is, as far as every experiment we've ever run can tell, completely transparent to every form of light we know how to detect. For decades, physicists have proposed candidates for what dark matter might actually be made of, and one by one, most of them have run into serious trouble. The earliest guess was that dark matter might simply be ordinary matter that's hard to see. Dim stars, rogue planets, black holes drifting through the galaxy. Astronomers even gave these hypothetical objects a name, machos, short for massive compact halo objects. But careful surveys looking for the gravitational fingerprints these objects would leave behind found nowhere near enough of them to account for the missing mass. That door mostly closed. The leading replacement idea became WIMPs, weakly interacting massive particles, a hypothetical new type of particle that would rarely interact with ordinary matter at all, slipping through entire planets essentially unnoticed, which is exactly why it would be so hard to detect. Physicists built extraordinarily sensitive detectors, buried deep underground in old mines to shield them from cosmic ray interference, specifically designed to catch the rare moment a WIMP might bump into an atomic nucleus. Some of these experiments used tanks of liquid xenon, cooled to extreme temperatures, sitting under kilometers of rock, waiting patiently for years at a time for a single faint flash of light that might signal a collision. After more than 2 decades of increasingly sensitive experiments, we still haven't found one. Not a confirmed detection. The most sensitive detectors on Earth have ruled out huge swaths of where WIMPs were expected to be, without finding anything. That doesn't mean dark matter isn't real. The gravitational evidence for it is overwhelming, showing up consistently in galaxy rotation, in the bending of light around galaxy clusters, and in the large-scale structure of the universe itself. One of the clearest pieces of evidence comes from a cosmic collision called the Bullet Cluster, 2 galaxy clusters that smashed into each other millions of years ago. The visible gas from the collision slowed down and piled up in the middle, exactly as you'd expect from ordinary matter colliding. But when astronomers mapped where most of the gravitational pull was actually coming from, using the way the collision bends light from galaxies behind it, they found it had sailed straight through the collision, mostly undisturbed, a strong sign that whatever is producing that gravity barely interacts with ordinary matter at all, exactly as dark matter would behave. What it means is that after 50 years of searching, we still don't know what 85% of the universe's matter actually is. We know it's there, we know exactly what it does. We simply don't know what it's made of. As if an invisible form of matter weren't strange enough, in the late 1990s, astronomers discovered something even harder to explain. Physicists expected that the universe's expansion, set in motion by whatever event started it all, should be gradually slowing down over time. Gravity, after all, pulls things together, so it should be putting the brakes on cosmic expansion the way it slows a ball thrown into the air. Instead, when astronomers measured the brightness of distant exploding stars called supernovae, reliable cosmic distance markers because they tend to reach a very consistent peak brightness, they found the opposite. The expansion of the universe isn't slowing down. It's speeding up. Something is actively pushing space apart faster and faster, with more force the longer time goes on. This was such a genuine shock to the physics community that the researchers who confirmed it were awarded the Nobel Prize in Physics in 2011. Many scientists had expected the data to eventually reveal expansion gently decelerating, exactly as gravity would predict. Instead, two independent research teams, working separately and half expecting to disprove each other, arrived at the same startling conclusion. We call this mysterious force dark energy, and it's even less understood than dark matter. It makes up roughly 2/3 of the entire energy content of the universe, dwarfing both ordinary matter and dark matter combined. And unlike dark matter, we don't even have a solid physical mechanism to point to. It might be a fixed property built permanently into the fabric of empty space itself, sometimes called a cosmological constant. It might be something more dynamic, capable of changing in strength over cosmic time. Nobody currently knows for certain, and every proposed explanation runs into its own serious theoretical problems, including one famously described as the worst prediction in the history of physics, where a straightforward quantum mechanical estimate of the energy of empty space overshoots the observed value by many, many orders of magnitude. A gap physicists still haven't fully resolved. Between dark matter and dark energy, roughly 95% of everything in the universe is, quite literally, something we cannot currently explain. We've built a remarkably successful model of the cosmos on top of two things we don't understand at all. And in part two, we're going to look at the cracks that are starting to show up in that model. Cracks that some physicists think might be pointing towards something we haven't even guessed at yet. In part one, we saw that 95% of the universe is made up of two things we still can't fully explain: dark matter, an invisible mass holding galaxies together, and dark energy, a mysterious force accelerating cosmic expansion. You'd think with a model that's successful at describing what we observe, the picture would be settling into place. Instead, the closer we look, the more cracks start showing up. And some of those cracks are becoming impossible to ignore. One of the strangest problems in modern cosmology has a name: the Hubble tension, named after the same expansion rate Edwin Hubble first measured a century ago. There are two independent ways to measure exactly how fast the universe is expanding today. One method looks at the cosmic microwave background, the faint afterglow of the early universe, and works forward, calculating what today's expansion rate should be based on the conditions of the infant cosmos. The other method looks directly at nearby stars and galaxies today, using a chain of what astronomers call standard candles. Objects like Cepheid variable stars whose brightness we understand well enough to calculate distance directly, working from present observations alone. These two methods should agree. They're measuring the exact same quantity using two completely independent techniques built on completely different physics. For years, physicists assumed that as our instruments got more precise, the small disagreement between them would shrink and eventually disappear, the way most minor scientific discrepancies eventually resolve themselves once measurement error is squeezed out. It hasn't. If anything, as measurements have become more precise, the disagreement has become more statistically significant, not less. The two methods now disagree by an amount that's getting harder and harder to explain away as simple measurement error. This matters enormously because it suggests one of two things. Either there's a subtle, undiscovered error somewhere in how we're measuring cosmic distances, entirely possible, but increasingly hard to locate after years of scrutiny from multiple independent research teams using different telescopes and different techniques. Or our fundamental model of the universe, the one built on dark matter and dark energy, is missing something. Some new physics, some new ingredient that would explain why two correct measurements are giving two different answers. Some cosmologists have proposed that dark energy itself might not be perfectly constant, but could have behaved slightly differently in the early universe than it does today. A small tweak that could potentially resolve the tension without throwing out the rest of the model. Others suspect the answer might involve a new, currently unknown particle active only in the universe's first few 100,000 years. Neither idea has been confirmed, and both remain active areas of ongoing research. There's another anomaly worth mentioning, found not in the expansion rate, but in the cosmic microwave background itself. That ancient afterglow of light released when the universe was only a few 100,000 years old. The cosmic microwave background is remarkably uniform in every direction, varying in temperature by only tiny fractions of a degree. But one region, discovered in data from the WMAP and Planck satellites, stands out, a patch of sky notably colder than its surroundings. An anomaly astronomers have nicknamed the CMB cold spot, spanning a region of sky far larger than would ordinarily be expected from random statistical variation alone. Most explanations proposed so far are relatively mundane, perhaps an unusually large, empty region of space along that line of sight, called a supervoid, or causing light passing through it to lose a little extra energy on its way to us as it climbs out of a shallower than normal gravitational well. But some of the proposed explanations are much stranger, including speculative ideas that it could be evidence of a collision, sometime in the deep past, between our universe and another one entirely, if something like a multiverse actually exists. To be clear, this remains genuinely unresolved and actively debated. And the more exotic explanations are speculative rather than confirmed. But it's a useful reminder that even the most carefully mapped structure in cosmology, the oldest light we can see, still contains features nobody has fully explained. So where does this leave us? Between the Hubble tension, the cold spot, and the simple fact that we still don't know what dark matter and dark energy actually are, physicists are taking a few different paths forward. Some believe the answer is a new particle or a new force still waiting to be discovered, something that would resolve the Hubble tension and finally explain dark matter's identity in one unified stroke. Others are looking at whether our theory of gravity itself needs modification at the largest scales, an idea sometimes called modified gravity, which tries to explain galaxy rotation without invoking any invisible matter at all, though this approach has struggled to explain some of the other evidence for dark matter, like the bullet cluster we discussed in Part 1, just as well as the Standard Model does. And a smaller, more radical group of physicists wonder whether we're missing something even more fundamental, some assumption baked so deeply into our models that we've stopped noticing we're making it at all. The way earlier generations of scientists didn't notice they were assuming the universe had always existed until evidence forced them to reconsider. None of these explanations is confirmed. That's precisely what makes this one of the most exciting open problems in physics today. Not because we've failed to understand the universe, but because we've understood it precisely enough to notice that something doesn't quite add up. So the next time you look up at the night sky, remember what you're actually seeing and what you're not. Every star, every galaxy, every glowing nebula you can point a telescope at makes up less than 5% of everything that's actually there. The rest is invisible, unexplained, and quietly shaping the structure of the entire cosmos, whether or not we ever figure out what it is. We've built an extraordinarily precise, extraordinarily successful model of the universe. And that model runs almost entirely on two things we don't understand, plus a growing list of cracks that our current picture can't quite paper over. That's not a failure of science. That's exactly what the frontier of science is supposed to look like. A map with a few places clearly marked unknown, waiting for someone to fill them in. If uncovering the universe's best-kept secrets is your kind of thing, subscribe, because there's a lot more of the map still left to explore.